In part 3, I explained SNE, and now I focus on t-sne and its variants such as conditional t-sne and variational autoencoder t-sne, these two articles. So there are lots of ways you can classify dimension reduction techniques. And by the way, in my book, chapter Dimension Reduction and for financial markets, I have explained different techniques for dimension reduction. So this is just one of ways. And t-sne is very popular together, and also UMAP they are very popular for visualization for practical reasons. And so dimensionality reduction for visualization. So most of the time people start with PCA, principal component analysis, and then even they combine it with t-sne or UMAP. So in visualization for single cell RNA sequencing, which I really like, is that nowadays instead of just a single cell, we can have thousands of cells. So if you have a tissue of your body, so you have a single cell, and then you have some techniques such as in microfluidics. So we don't care about it. We just care about the sequencing, that after sequencing we can do a dimensionality reduction to reduce the dimensions, because as you see, we could have thousands of genes. We could have, for example, 20,000 cells. As you see, the feature size, the number of genes which are feature size, is huge. So you should reduce the dimensionality in order to visualize it like this. So you could use UMAP, you could use t-sne, and so after some preparation, you can have this matrix, which is just counting. For example, for cell 1, we have 22. The expression of genes, the counting. If you count the reads for gene 4 is 22. So, for example, in Netflix, you have lots of movies. Instead of genes, you have movies. And instead of many cells, you have some users, some customers that watch these movies. So all of them are the same. So people use non-negative matrix factorization and many techniques. So all of the techniques of dimensionality reduction could be used. But for our purpose, let's focus on just t-sne. So because the dimension is huge, people usually start with PCA in order to reduce as much as possible, and then they use t-sne, and then they do 2D visualization. So again, this is our matrix. And as you see, we have two factors, t-sne dimension 1 and t-sne dimension 2. And just recalling and extending lecture 3 of the current playlist, as you see, this great article is published after the 2002 article that they talked about variations of stochastic neighbor embedding. And then in 2008, they continued, and so it's just saying that the probability that I pick J given I, or the probability of picking J given I in the transformed space. So this space is just maybe 2-dimensional, 3-dimensional, but this space is huge. For example, 20,000 dimensions, 20,000 genes, or 20,000 movies. And the cost function for SNE is just the KL divergence between any of these. And the SNE cost function focuses on retaining the local structure. And that's why it produces some problems that I will explain, such as crowding. As you see, crowding is, I show it in just in this slide. So x1 has neighbors x2 and x4. x1 has neighbors x2 and x4. So no problem here. Then let's look at x2. x2 has neighbor x1 and x3. That's okay. Let's look at x3. x3 has neighbors x2. This is okay. And x4. But this is not okay. So this is a problem. We call it crowding problem. So if you just focus on local properties, preserving the local distance, you will have problems in the global structure, because unlike variational autoencoder that preserves somehow the global structure, in SNE, unfortunately, in t-sne, they can't preserve the local structure. So let's come back to this KL divergence. So I said that this is the cost we want to minimize. So and the perplexity is just a smallest measure of effective number of neighbors, because it's very bad if you say in advance how many clusters you should have, and H here is the entropy. And so we want to minimize the cost function for SNE. This is the Kullback-Leibler divergence between distribution P and Q. So if you take the derivative because you need it in the gradient descent algorithm, and this is just the momentum. So this part is just the gradient descent, and this is an advanced gradient descent. Think about it like that. And the T-distributed stochastic neighbor embedding tries to unify and simplifies everything. So we have just one P and one Q. So everything is the same. And so the derivative is somehow easier to verify, easier for the algorithm. And I explained crowding problem. And they noticed that if they use t-sne instead of SNE, so if you have student T distribution, you could have less problems with this crowding problem, and they have realized it in practice. So this is the gradient, and they visualize it in their article. They show, for example, in MNIST data, all zeros are around each other. And so in 2019, great researchers from Ghent University, like Geoffrey and these two amazing researchers, they noticed that we can focus on capturing complementary information if you have prior knowledge. So what do you mean? So this is the same thing. We have P and Q, but instead of P and Q, we want to minimize the Kullback divergence between P and R. So the Kullback divergence between P and R should be minimized. But unfortunately, this is a non-convex problem, so that they use a smart VAE, which is a random restart for gradient descent, and which is a very good VAE. And so this is the gradient, and Z is this variable. And after that, in 2020, people in Max Planck notice that they can combine VAE, variational autoencoder, with SNE, because this cares about the global structure, but SNE cares about the local structure, preserving the local distances. So if they combine it, they have this method that they combine the global and local information. And this is not difficult. You have seen several times the elbow in variational autoencoder, or any similar approaches in variational inference. For example, in stochastic variational inference, several places you have seen elbow. And this is the added objective function, the SNE that we add, which is just the expectation of SNE. And so this objective cares about local preservation, let's say, and this is the global. So it preserves the global properties. So by combining them, we hope that we can reduce that crowd problem that I explained. Oh, by the way, this is my favorite Belgian mathematician, Jan Bergane, the Fields medalist in 1994. The reason I like him because I enjoyed his ideas about metric embedding. And by the way, you can watch my playlist in metric embedding. And I explained, I think, two or three articles of Jan Bergane. And that is very beautiful. And of course, he's more advanced than what computer scientists do. And he works on Banach spaces, which is much general space. And it is much more abstract than what computer scientists can do. So, as you see, I explained all of the things, all of these beautiful things. The reason that I like to show you this, because if we focus on the applications of machine learning in healthcare, we can help humanity. We can help people by curing cancer, by removing many diseases, many cancers, just by analyzing these things. Because as you see, the order is huge. The number of features is huge. You can have 20,000 genes, for example. And each gene has its own coordinates. So it's a huge space. But somehow we want to see, for example, which genes are more responsible for Alzheimer or let's say any disease, any cancer, any problem. And this is a good way to visualize it. And the article of those people in Ghent University in Belgium is interesting because if you fix some prior information, you can focus on the complementary, which is more beautiful and more important for you to discover. So they created conditional Tsne, and of course some people start with PCA, principal component analysis, but it's a naive algorithm. You could use variational autoencoder together with t-sne in the article that I explained, but I want to point out that the cost function for SNE is very interesting, and in the minimization problem, you see that the derivative is very explicit, so we have no problem, and it tries to reduce crowding problem, although it cannot fully remove it because, by the way, you are just focusing on local preservation and not global preservation. So you could expect that you have some crowding problem even after t-sne. And so these guys introduced t-sne instead of SNE, and a very good visualization. So t-sne is very popular now in computational neuroscience as well as computational biology and many other fields that you want to focus on a kind of dynamic way of visualizing. For example, sliding some variable and graphically these things move or repel each other or come close to each other, and you can see the effect of all of these things through. And the conditional t-sne, as I said, tries to also include the prior knowledge. If you have a prior knowledge, for example, maybe from your experiments, you already know which two cells are similar to each other, so you can take advantage of that. And the objective function is non-convex. No problem, we can use several techniques such as, I wrote an article about this non-convex optimization. I remember I used successive approximation, like majorization, minimization, So it's a kind of, if you have a non-convex problem, you can just approximate it. You try to make it convex, and so at each time you try to make it convex, even if it is highly non-convex. In neural networks, everything is non-convex most of the times, unless it is very trivial and easy. So you could use these successive approximation techniques. But another smart way is by these researchers in Belgium very beautifully. They use random restart, because they know that the complexity of your function space is not that much. If you can remove the number of layers, you can remove the number of variables in neural networks to reduce it. And here, because the objective function is not that much non-convex, you can always use some random starts. Why do we use random starts? So because if you start from here at a random point, you converge to this point, which is the global minimum. But if you start from, let's say, this point, you may converge to this point, which is not a global. So it's a semi-local minimum. And that's why you need such lots of these points to discover all of these valleys and all of these very sharp areas that are deep valleys, because most of the time you cannot find such a flat area, such a beautiful. Of course, this is great for generalization, as I've explained in my playlist for deep learning in 2032. So that is my point. And the other one is, let's combine global and local information. As I said, variational autoencoder are very good because they have they have encoder, and we have some latent variable, let's see z. And they try to preserve, of course, in the context of semantic hashing, I have explained it how to use mutual information to preserve these distances. And but this is another way. Of course, variational autoencoder is naive in comparison to that semantic hashing that I explained in that beautiful article. And of course, they have decoder here, and they reconstruct that. But they combine it with tsne. As you can see, they have some latent variable, and they just need to add one more term, which is tsne. And alpha measures how much, for example, you care about the local. For example, if alpha is high, you care about local preservation more than global preservation. So it's a hyperparameter that you could use in your research.